Okay, welcome back, everyone. I think we're going to get the next session started. I'm Hilary Corlett, going to be one of the chairs for this session on deeper diagenesis, and Jack Stacey will be my co-chair. Jack, did you want to start?
Oh, sorry, yeah. Sorry, yeah. So I just thought I'd quickly remind the audience that recording of these presentations is forbidden. Presenters are going to have 12 minutes, 10 minutes, they're going to get a 2-minute warning. And then there will be 7 minutes after that for the questions. So first of all, we have Wenwen Wei from the University of Bristol. And their talk is going to be on the creation of microrhombic calcite and microporosity through deep burial basinal flow processes driven by plate margin abduction, a realistic model. So Wenwen, can you please share your screen?
Oh, yeah.
Great, we can all see that.
Shall we start? No.
Looks good.
We can see that fine, yeah.
Shall we start? No. Oh.
Yes, you can start.
Oh, yeah. Thank you for introducing me. In this presentation, we wanted to talk about microporosity and microrhombic calcite, which is extensively developed in Jurassic and Cretaceous carbonate over the Middle East. But the causative process remain poorly understood, making prediction very hard. The isotope constrains the salinity and the temperature of fluid that form the microrhombic calcite at the time of development to ophiolite abduction. We use in this study we use reactive transport modeling to evaluate the proposed compaction flow mechanism. In addition, we also evaluate the role of fluid mixing in burial condition to the development of microrhombic calcite and microporosity. Our research data was come from over 13 produced fields in UAE. Mohammadi is we focused on Mohammadi, which is a major reserve unit in this area with over 15% microporosity and sitting layer cake stack of Permian to Cenomian limestone. Isotope data show that microrhombic calcite formed from basinal brine at 15 to 19 degrees C. Burial history model shows that this formation happened in depths of 600 to 1200 meters during late Cretaceous, which coincided with the plate collision and ophiolite abduction. Our hypothesis links the microrhombic calcite to the collision, plate collision and abduction. During ophiolite loading, the rapid burial of the Mesozoic carbonate to 10 kilometers beneath the slab could cause the flow of basinal brine from east to west drawn by tectonic compaction. We investigate this. We use a hydromechanical model to investigate this compaction flow. We add a hydromechanical result as input to the reactive trace model to simulation the formation development of dissolution and causative dissolution and precipitation caused by compaction fluid. And then we compare our simulation result with observation data to test the conceptual model. Our hydromechanical simulation use CMJ and JEM to simulation the geomechanical process called to simulation the geomechanical process of rapid burial over 5 million years, which copying the strain with pore pressure and compaction flow. The The hydromechanical result shows that the compaction occurs at mostly at less than 4 kilometers barrel. The most fluid was come from the east beneath the obducting slab, but the total fluid flux increased from east to west during the cumulative input from compaction across the subsiding plate margin. We use this could give the input to the RTM simulation, our reactive transfer simulation, because our RTM code cannot simulate the geomechanical process. So we injection fluid into every cell to represent the compaction fluid by power to repair the compaction fluid caused by the power decrease. Our general injection rate was the over space at the time our injection rate or injection is calculated as the decrease of porosity over time that simulated by geomechanical results. This is our baseline simulation, which is 3 times seawater fluid with 1 mole per kilometer CO2. The mineralogy is 100% calcite. During upward compaction fluid, there is the compaction fluid was projected upward fluid at cooling. The calcite dissolution during the upward causes the calcite the alteration of some before mentioned. This alteration mainly occurs in this area, which is reflects the balance between cooling and fluid flux. The alteration is most focused on 3 to 5 kilometers, but the net increase of porosity is very small. In addition, the moderate temperature is much higher than the 15 to 90 degrees that get from clump isotope test. We also, by varying the fluid CO2 concentration from to 1 magnitude lower or to increase to the CO2 saturation, gives only change on alteration and have no effect to the distribution. We also test the mineralogy by adding a mineral amount of hydrite and dolomite. The result shows that for different CO2 scenario, the result shows that it's have a less show that no further increase of porosity can be observed of distribution. Our result shows that during upward flow that comparison flow can mainly causes the calcite dissolution. If we look at the relationship of calcite solubility with pressure at the temperature, we can see that cooling will cause the increase of calcite solubility and cause the dissolution, but pressure decrease will cause the decrease of calcite solubility and cause the precipitation. So during upward flow, compaction upward flow, the pressure and the temperature will decrease, both decrease. So which means that the dissolution and dissolution and precipitation both will happen and cause the precipitation, dissolution and reprecipitation process, right? But why our result, RTM result suggests that only dissolution could happen. So we plot the the varying of pressure, the temperature during this upward upward flow of fluid. This red line is how the pressure and the temperature will change during upward flow, which shows that the pressure decrease have a very small impact to the calcite solubility at the final, but mostly impacted by the temperature decrease. The final result is dissolution of calcite dissolution. We also can see how the calcite dissolution will influenced by the CO2 concentration. The maximum dissolution occurs at intermediate CO2 concentration, not a higher or lower one. This can be also consistent with theoretical research from Dwyer and Lee, which shows that the maximum dissolution occurs at a CO2 concentration less than saturation. Our result of the simulation result shows that the microporosity
2 minutes.
Compaction cannot cause microporosity formed at right place at temperature. So we to think about consider another scenario. If compaction fluid cannot only cause the compaction fluid overlight in the Mohammadi, but also can enter in the underlying formation. This compaction fluid may release to the Mohammadi along faults in this area. So could this cause the calcite microporosity, microrhombic calcite formed at the right place of temperature? So we wanted to investigate. So we use a more detailed, build a more detailed mixing model that focuses on the shallow and this part of basin model. And we tested, simulated a serious variation by injection rate, injection temperature, and the fluid composition for with varying with different H2S concentration in injected flow and different CO2 concentration in formation flow. Our results show that by injecting a fixed volume injection flow, the fluid injection and mixing will cause the dissolution to distribution into different area. The large injection rate will cause the dissolution occurs in a large area, but a lower amount of dissolution. If this figure shows that how the injection rate was changing, that shows that the lower injection rate have a large dissolution, but increased injection rate cause more slow dissolution. We think this is related to the nonlinearity of calcite solubility. So if we injection at a higher area, it will extend to the large area, but which means that the injection flow have a low ratio compared to the formation flow. So this give a lower calcite solubility on the saturation degree. If we injection at a lower injection rate, it will give a
we just need to finish up. Sorry, we're at the end of time here.
Oh, awesome. This causes more dissolution. Another finding is that we injection higher CO2 H2S concentration into the higher CO2 concentration will cause the precipitation, because the fluid can only dissolve a limited amount of both these two gases. This will injection a higher H2S into formation will cause CO2 degassing and precipitation. This also independent to the injection rate.
Okay, yeah, I think we have to end there because we've just gone over time there. Sorry.
Oh, well.
Okay, so thank you very much, Wenwen. We're just going to head into questions now. So we do have some minutes for questions. Just a reminder that all speakers should be thinking about wrapping up at 12 minutes exactly, otherwise your screen will get cut off. And you'll get the 2-minute warning when you've hit 10 minutes for your presentations. So for questions, anyone can send their questions to the chat. It is now open. Just ensure that you're sending your question to everyone. And we can take questions over the next 4 or 5 minutes. Any questions? Yeah, I don't see any questions in the chat yet. So I'm just curious about the, so in this study, you're injecting both H2S as one case scenario and CO2 as another, is that correct?
Oh, yes. No, we just injection the H2S, but formation fluid, we changing the CO2 concentration. In formation water, the injection.
Oh, okay. Sorry. Okay, yeah. So in the formation water, it's
changing the CO2 concentration.
Okay, changing the CO2 concentration. Okay, thank you. And I do see we have a question now from Kathy Hollis. Kathy says, "Thank you, Wei. It is good to see this system being modeled. Could you say a little more about the fluid you are injecting through faults? Might these be brines that are related to hydrocarbon change or charge? Was that meant to be? So could you say a little more about the fluid you are injecting through the faults, Wei?
You mean the fluid composition or what? Fluid composition.
Are they brines related to hydrocarbon charge?
We don't consider hydrocarbon charge of these brines.
Okay, so your brines you're injecting are, I mean, if I understand, I think the brines you're injecting have different concentrations of CO2, you mentioned? And
oh, yeah, yes, have different H2S. In injected fluid, we have a certain small CO2 concentration.
Oh, and I see Fiona says the brines are 3 times seawater, have variable H2S concentration. Okay, yeah. And I see we have another question from Alexis. Thanks. I see the porosity was only impacted by 0.1. Do you suspect any impact on permeability in the process you have modeled?
I think with this small porosity, the permeability didn't have much impact. During our simulation, we actually didn't update the porosity permeability change during the porosity because we injection the fluid. We consider that this our fluid is mainly controlled by the injection because we have fixed the battery pressure and the fluid flow was mainly controlled by the fluid injection. So we didn't update this permeability change because we think this may have some impact to the fluid flow, and we wanted to compare our fluid rate with the simulation result of geomechanical model. So we did not update this.
Okay, great. Thank you very much for your presentation and for answering questions. We're going to move on to our next speaker. Jack, did you want to introduce our next speaker, please?
Yes, so next we have Sahar from the University of Kansas, and they're talking about the diagenetic impact of basinal and hydrothermal fluids in the Mississippian rocks of the southern mid-continent of the USA. So Sahar, could you please share your screen?
Yes. Do you see my screen now?
Yes, we do. and we can hear you just fine as well.
Great. Hello, everyone. I am Sahar Mohammadi, Assistant Scientist at Kansas Geological Survey. The research that I'm presenting today is from my PhD dissertation, deals with the genetic impact of basinal and hydrothermal fluids in the Mississippian rocks of the southern midcontinent of the United States. This research was supported by Oklahoma State University and Industry Consortium. We thank the companies for funding and donating samples for this study. And I also would like to acknowledge my PhD committees, Doctors Kevin Shelton, Mike Grammer, and Jim Pocket. Mississippian rocks in the southern midcontinent of the United States affected by multiple events of deformation and diagenesis. This has resulted in a complex diagenetic history involving petroleum migration, thermal alteration, and MBT mineralization. It is important to note that Tri-State Mineral District at the conjunction of Kansas, Missouri, and Oklahoma is one of the largest MBT districts in the world that hosted by Mississippian rocks. Mississippian carbonates were significantly affected by regional hydrothermal fluids. Movement of these fluids related to gravity and seismic pumping resulting from a watchtower orogeny. This dynamic is globally applicable for other foreland basins. This study applies petrography, fluid inclusion, and isotope geochemistry to examine the effect of early and late diagenetic fluids and identifying the composition and source of these fluids regionally in Mississippian rocks. Of particular interest is the effect of late diagenetic fluids on the evolution of porosity and thermal history of the region as it relates to petroleum migration. This is a map showing my study area, which divided in two study areas. The first study area involves subsurface, mine, and outcrop samples from Cherokee Ozark platform. And the second part is involved with subsurface carbonate in north central Oklahoma. And the yellow dots are my sample locations. Mississippian in United States divided in 4 stages: Kinderhookian, Osagian, Myrmekian, and Chesterian. My research covers all of these stages. However, we lack stratigraphic data to constrain the age, especially in central Oklahoma. To understand the diagenetic history of Mississippian rocks, I integrated a number of tools. I was primarily interested in sampling rocks with fractures, bogs, and porosity filling cement. And I collected them from cores, outcrops, and mine samples. Also, I conducted petrography and catoluminescence to define lithology and cement paragenesis and the relationship of carbonate cement with other diagenetic events. I conducted fluid inclusion microthermometry to determine salinity and temperature of late diagenetic fluids. And also used ultraviolet epifluorescence to identify petroleum inclusion. Carbon, oxygen, and strontium isotope geochemistry were conducted to determine the type of diagenetic fluids that affected rocks. Intra and intergrain porosity, fractures, widened solution channels, and rock filling, calcite, dolomite, and quartz observed in our samples. The upper left-hand side is an example of saddle dolomite in Tri-State Mineral District. Below is intragrain porosity filling in rugose coral with early and late calcite cement. The upper right is an example of widened solution fractures filling with late calcite and quartz in Osage County, Oklahoma. And below right is intragrain porosity filled with early calcite and late saddle dolomite cement. I also observed one-phase and two-phase fluid inclusions, vapor and liquid, in open space filling cement such as calcite, dolomite, and quartz. are used cooling and heating process to obtain their salinity and minimum trapping temperature of the paleo fluids, which we call it homogenization temperature. The upper left is an example of primary fluid inclusions in calcite cement, and below is the assemblage of primary and secondary fluid inclusion in calcite. The upper right shows the assemblage of primary fluid inclusion in quartz, and below is a primary fluid inclusions in dolomite cement. Carbon and oxygen values plotted and shown here, and fields are previous published data. The data are from North Central Oklahoma in the left, and the right is from Cherokee Ozark platform. In both of them, we see a skeletal grain and early marine cements appear to be in equilibrium with Mississippian seawater, as it located here and here. Intermediate blocky pore-filling cement and southern dolomite cement can be interpreted as an equilibrium with fresh phreatic water with seawater. And later stage of blocky calcite cement in both areas, but consistent with precipitation from hydrothermal fluids. This interpretation is consistent with our fluid inclusion data. The low carbon values of late diagenetic cements are consistent with introduction of petroleum by late diagenetic fluids. Low carbon values in North Central Oklahoma are probably associated with hydrochemical sulfate reduction related to petroleum migration. In this plot, strontium versus oxygen isotope shown, and the high strontium values are in two study areas indicate a fluid inclusion interaction with continental basement or sedimentary rocks derived from the basement, or such as arkose or shale. This slide also shows the fluid inclusion data. The data are based on salinity versus homogenization temperature. The fields are previous published data from Tri-State Mineral District area. These data show two distinct end members based on salinity, very saline fluid in two areas and lower salinity. The temperature on both fluids vary from 50 to 175 degrees Celsius, which can be considered as moderate to relatively hot diagenetic condition. So the isotope and fluid inclusion data both help us to understand the fluid flow migration alterating Mississippian rocks. Based on that, there are two general models fluid flow to apply this to this study. The first figure in the top shows advective fluid moving laterally across the basin by gravity-driven flow model through Cambrian Ordovician strata. Some of these fluids in some locations, such as Oklahoma, they move up along the fault and fractures and interact with the rocks along their pathways and mix with dilute resident fluids, possibly originating from Mississippian seawater as shown in the second figure. Our PhD student, Andrew Hollenbach from University of Kansas, who will present the next slide, will talk about the localized fluid migration by fault and fractures, as well as regional fluid flow into aquifer system. He's using uranium lead dating technique to reveal the mechanism and drivers of hydrothermal fluid flow. So in summary, primary porosity in carbonates in Cherokee Ozark platform was retained until late diagenetic history. However, in North Central Oklahoma, most of intra and intergrain porosity was filled with early diagenetic cement. Fractures and breccias provided additional porosity filling by later diagenetic cement. The saline hydrothermal fluids that invaded Mississippian carbonates are sourced by underlying Cambrian Ordovician and move up along the fault and fractures and displacing the less salient resident fluid.
2 minutes.
Sure. This fluid movement probably occurred during a Ouachita orogeny and coincided with petroleum migration into Mississippian rocks from underlying Devonian Woodford Shale. These are 3 papers from my PhD dissertation that published in AAPG Memoir Special Publication, and they are available online. With that, thank you very much, and I will take any questions.
Great, thank you very much, Sahar. If you wanted to scroll back to advertise your papers a little more, we could keep that screen up so people can have a chance to write those down. That's great, thank you. And the chat room is now open. Just a reminder to send your questions to everyone, and we can take any questions you may have now. And I was gonna see if my co-chair had any questions for you to start us off. Jack?
Yes, so Sahar, thank you for a really great talk. I really enjoyed that. What do you think, in terms of the regional scale fluid flow, how do you think, you showed your kind of dolomitization model, but how do you think it kind of fits in terms of the more regional scale things, and what kind of geochemical data would you need to kind of reconstruct that?
If I could understand your question, well, you're asking that how this fluid flow works and applies for regional scale, right?
Yeah, so sorry, my question wasn't very well worded, but what I really was getting at was how does your model kind of fit into the regional scale fluid flow, and how can you kind of trace that fluid flow as well?
Yes, so what we're doing here is in eastern side of the study area, as shown in Ozark, Cherokee, we have shallower, we are at the shelf margin. But however, in the central Oklahoma, we don't have that much aquifer in the Mississippian. So that this fluid migration was in the Ordovician Cambrian, but if there was any local fault and fracture, these fluids could come up and displace the Mississippian water. What Andrew, my student, is working on it now, working mostly in regional fluid migration. Here he will explain it more, that there are several tectonic drivers that applies for this study that can move these fluids in different locations with a different timing. We are still working on it, on getting the absolute dating to see which tectonic activities and drivers work on the southern mid-continent in the regional scale. I hope I could answer your question.
Yeah, that was great. Thank you.
Great, thank you, Sahar and Jack. We have a question coming in from the chat from Cole McCormick. Hi, Sahar. On slide 8, you showed your stable isotope for replacement dolomite and saddle dolomite. Do you see any differentiation between these phases on a sample by sample basis? Or potentially if you were to zoom in and show a narrower region on your x-axis?
So let me read the question again.
So he's asking if you see any differentiation between phases, your replacement dolomite and satellite dolomite phases on a sample by sample basis. Is it one big clump, or do you see variation within the sample sets of replacement dolomite and saddle dolomite, I believe is what he's asking.
Okay. Not really, like most of the, as it's shown here, like planar replacing dolomite and planar, as you see here, some of them are most of the replacement dolomite are involved with the equilibrium with the mixing zone, like freshwater and seawater. And saddle dolomite was also not really, not the sample by sample.
There's not really a big difference between. Okay. Okay, thank you. And I think we still have a couple more minutes here. I was going to ask, you did mention seawater briefly in your model, right? So, but I wasn't sure exactly, were you invoking that in terms of timing? Are you invoking seawater flux down the convection down the fault at all? Yes?
Yes, in some places might be, but what I'm saying here that the hot fluids coming along the fault and fractures and probably displace this seawater mixed with this seawater. This is why we get different salinity and different temperature.
Okay.
But it happens in several locations that we have those sinkings in mostly Kansas.
Right.
Which was not part of my, that section was not part of my study, but there's some other publications that's saying that.
And what is the size of your dolomite bodies? Just curious.
What do you mean by size of?
So I'm just curious the size of sort of around these faults. You have them kind of forming around these faults. So just wondering about the scale.
Unfortunately, I don't have the scale for that. So mainly I was focusing on any fractures or vogs feeding with cements. So technically on my samples in Oklahoma, I didn't see any saddle dolomites. It was there, but it was not in my samples. However, we move up to the east side where we have tri-state. I observed more saddle dolomites feeding fractures or vogs. Andrew in the northwest of Oklahoma observed saddle dolomites in his samples. So most of this porosity in the central Oklahoma, most of this porosity earlier filled with earlier calcite cements. And later fractures or porosity filled with calcite and later dolomite. However, much of the porosity in the Ozark Cherokee, in the eastern side of the study area retained till the late Diagenetic and then filled with later cementation, such as dolomite, calcite, and quartz.
Okay. Okay, interesting. And I think maybe just one quick one. Your porosity, you said, sorry, when did you say the porosity forms? Do you think late or early was it?
Oh, what I mentioned that, to bring the map again.
You just have one
here
minute.
in the eastern side of the study area, much of the porosity, early porosity, retained till later diagenetic events, and then filled with calcite, dolomite, and quartz. However, in the second study area in central Oklahoma, the earlier porosity filled with earlier cementation. And only vogs and fractures filled with later cementation, later diagenetic cements.
Okay, thank you. Okay, great. Thanks very much, Sahar. That was very interesting. And I believe you said that we will be hearing, yes, we will be hearing next on an expansion of this study. So talking more on the regional scale. Jack, did you want to introduce the next talk?
Yes, so next up we have Andrew Hollenbach, who's also at Kansas, and his talk is entitled Tectonic Drivers of Hydrothermal Flow Through US Midcontinent Carbonates. Andrew, if you'd like to share your screen, please. Great, we can see that. We can't hear you yet, though.
Okay.
Oh, there we go. Okay, good.
Okay, good. Thanks, Sahar. Good talk there. My name is Andrew Hollenbach. As Sahar said, I'll be presenting a little bit of an expansion of her study. I'm working along with Sahar as well as Bob Goldstein and Andreas on this specific project here. What I'll be talking about today is tectonic drivers of the fluid flow in the Midcontinent US, and using this first a slide here just to give you an idea of where we are in the world. So here's the United States. My study area then is in the middle of it. And I've blown it up over here to show this figure, which has lots of fault lineaments there. So there's lots of structure that's antecedent, very old structures here. And so we'll be looking at this this figure quite a bit today. And on the bottom here, you can see I've laid out the outline for the presentation. And so we'll just get right into it, starting with the problem. So what we have here in the Midcontinent is an interesting problem in which we're finding these hydrothermal fluids are altering late in the paragenesis. And by that, I mean after significant burial. So if we do, look at the petrography and lay out a paragenesis, we find that really after stylitization, after other evidence of compaction is when these hydrothermal fluids are coming into the rocks. And by hydrothermal fluids, I just mean really warm, hot fluids being injected into colder rocks. And so where do we see it? Well, all of these red stars that you see on this figure here are places in the literature where we have documented evidence of hydrothermal mineralization, so minerals that are coming precipitating from hot fluids. So let's just take a look at a couple of them. Here in the tri-state area and Sahar just talked a little bit about this, is where we are, there's quite a bit of mining operations, and the pay dirt for those mines then is sphalerite and galena. And these are hydrothermal minerals that came in with these hot fluids. Looking at more of your sort of reservoir example, here's a thin section. The blue is where you have epoxy preserving the open porosity. And what you can see here is Baroque dolomite then growing into that open porosity, reducing the porosity. And that Baroque dolomite there is precipitated by hydrothermal fluids, as confirmed by fluid inclusion temperatures and comparison with burial depth temperatures. So looking at this sample here is from my study, and I'll point out where that is on the map here in just a moment. But I want to point out, this quote here is something I find pretty interesting. So Ernest in 1959 pens, "If the next 18 years provide as much new information as has become available in the last 18, then the answer to this 100-year-old problem may be obvious." So of course, I'm still trying to work on this problem, and I'm a good 50 years since then. So it's a long-standing problem, and that problem is really what's driving these fluids through the subsurface and what is that fluid flow pathway. And so just to look at this sample a little more closely, because this is really the sample I'll focus on, I'm just basically laying out the most direct way to show this later paragenesis. So after anhydrite, we have partial replacement with quartz, chalcedony, and megaquartz. And this, in the wider paragenesis, this is after stylitization and early silicification, as well as other early events of diagenesis. So these are all really later burial or post-burial events in which you have this chalcedony, then megaquartz, then calcite. So pretty clear here. I've been able to go in and look at the megaquartz and calcite fluid inclusions and have confirmed that these are precipitated by hydrothermal fluids well above burial temperatures. And so the objectives then for my project are to increase the database. What you're looking at is that same map. You can still see those red stars in which we know there's hydrothermal, we have evidence for hydrothermal mineralization in publications. And now we see these orange squares. Those are where I've been looking at samples, I've collected data. And then the blue squares are really what I'm hoping to accomplish over the next couple of years. So doing that, getting this data, I believe I'll be able to identify mechanisms driving flow and that fluid flow pathway. So here's where that sample is taken from. This is from an oil well, about 2,700 meters below ground surface. And so I think that qualifies for deep diagenesis in this case. So I just want to back out and just talk about tectonic processes. This is just really, I'm just going to focus on this one, because it's when you have these cratonal settings, it's a long history of tectonic events that can potentially drive flow. But I wanted to just focus in on the sort of obvious one here, which would be the formation of Pangea. So we call it here in this area the Ouachita orogenic belt. And this is, when Gondwana is colliding into Laurentia and forming this range here and this uplift. And so that topographic relief then could drive fluids through the basin, and I basically have a cross section then here going pretty close to that sample. This is just like your normal simplistic postage stamp cross section here of that. What you can see is this four-land basin of siliciclastics, the yellow, shedding off of the mountain range, and then below it the basically shelf and ramp carbonates that have been pushed down below that basin. And so the idea here would be that this event is capable of driving flow. So how would it drive flow? First idea here would be like just a basic, simple advective flow. And you can see these arrows are indicating sort of the flow direction away from that topographic high. It's basically a hydraulic head is being put on, and these deeper, hotter brines of the basin then are getting migrating up dip underneath base Pennsylvanian seal is what I'm showing here. And so just a very simple flow from topographic relief. The second hypothesis I want to talk about is what I call structurally plumbed advective flow. So you can see it's really the same. We're driving fluids advectively and due to the topographic relief. However, now I'm drawing it along these fault lineaments that were structures that were there at the time of the formation of Pangea. And so the idea here would be that it's following these sort of super highways of flow. And so again, if I was to draw that in cross section, well, it looks about the same. Of course, it would be along then structural damage that I can't show in this 2D cross section, but is able to be shown here. And then the third one I wanted to talk about today is what's called fault pump flow, idea of Simpson, who basically is giving this idea that if you have slip on a fault, then you're going to open up a space, and of course nature does not like that space there, so it therefore pumps fluids then directly up. And so what I'm showing here is a seismic interpretation. It's a wrenched flower structure that is penetrating deep into the basement being this interpretation here. You can sort of see that surface is the basement interpretation, and then these faults penetrating deep below it. And then that would be essentially pumping fluids directly up. So if I was to show that in cross section, we're kind of up on this, up towards the craton, the shelf, and the fluids are going to be coming directly up, triggered then by any reactivation of the faults. So how do I test this hypothesis, and how is this working? Well, the first thing I do is really enjoy petrography. I think that's a really important part of this. Spent a lot of time on the microscope establishing a paragenesis. And what's interesting that I'm finding is that almost no matter what sample I've looked at, what I see is that the hydrothermal mineralization is really petrographically or paragenetically late. And again, by late, I mean after significant burial. So I see lots of early cementation and then evidence of compaction. And then it's not until after that then that we start to get quartz, calcite, dolomite, and sphalerite if you're in the tri-state area that is coming in.
2 minutes, Andrew.
The fluid inclusion homogenization temperatures is really key. the expectation would be that if you have an advective flow model, then the deeper part is where you're going to see the hottest temperatures, and they should be cooling as they flow laterally. And similarly, you'll see these same signatures at delta 18O as well as radiogenic strontium. But really what sets this study apart, in addition to having all the data, is the uranium lead dating. And so just going back to the sample, again, it's right here. We're able to get a date on this calcite. And what we see, this is the Tara-Wasserberg plot here, is a well-constrained age of about 318 million years. And so when I see that, I'm thinking, hey, this is really looking good as a, having been driven by that event, by the formation of Gondwana, that mountain range did cause flow. And so, of course, that's not the only, that's just one sample location. We have the several locations. And what's fascinating is we're actually getting a spectrum of ages from that event, but also all the way down to just 5 million years ago, where there really isn't anything major tectonically going on. So we have evidence for fault pump flow, this one. We have evidence for advective flow. And once I fill in, I suspect I will likely have evidence of this structurally plumbed flow. And so I think what's really going on here is a complicated thing where the answer is yes, all of these are potentially happening. And hopefully by, at the end of this study, I'll be able to point out how, when is which. So the impact, differentiating these driving mechanisms, being able to identify when is it this mechanism versus when is it another, will really be portable to other cratonal settings that are similar. And then we look at flow pathways. Understanding that means you understand porosity evolution.
We're at 12 minutes, Andrew, so just wrap up.
Yeah, timing of hydrocarbon migration. And so, of course, we have better models, higher efficiency, extraction natural resources, and better predictive models. So I'll take questions.
Okay, great. Thank you very much. And that was really interesting. I have to admit, I didn't know the basin was that complex there. Geez. It's out of my comfort zone, but yeah, that was really interesting. Thank you very much. I see a question already in the chat from Cole McCormick. I like your concept of combining existing models. One of the challenges with squeegee flow is low fluid flux. Simpson hits the concept that you need some form of dilation to really pump these fluids. How do you reconcile negative flower structures in a compressional tectonic setting? Are you seeing evidence of transtensional tectonics, maybe just on a local scale?
Yeah, I think that's a really good question. So if like, for example, that seismic interpretation I showed there is that's exactly what I see. It's looks like a flower structure, which is really a wrenched flower structure on the local, at that local scale. And what I'm hoping is really to be able to tease out like, okay, this is this part of the, so say a negative flower structure may be where the fluids are coming up as opposed to this other side. So maybe it's cementing this side and not cementing the other. But yeah, I think that's exactly right. Those complexities matter. There's kind of a second part of that question, which is the temperatures, the rate of flow maybe not being enough. I think that's a good point. As the data comes in, it's becoming interesting. So like that cement that I showed that we have an age for, it is hydrothermal, it is hot, but it's not ridiculously hot. It's not like really high above normal burial. Whereas I think if you could go way north and be on a structure and actually have really hot temperatures. So yeah, there's a dynamic there that I think will help us sort out the mechanisms. Yeah.
Right. Okay. Yeah, interesting. Okay. Sorry, there's another question now from Kathy Hollis. So thanks, Andrew. That's really interesting. Sorry if I missed this, but are you able to see different mineral assemblages along different fault types or fault trends?
Different mineral assemblages. So that actually is really interesting. That my experience so far, looking at the you know, the cores I've been going through, you know, maybe half a dozen or a dozen, is actually that the paragenesis is remarkably similar across the whole area. So like, I go into a new core and think like, is this going to be different? What is the assemblage going to look like? And yet it's like the same. So it's like after stylitization, then you have, you know, maybe a hydrothermal dolomite come in and then a calcite. It just seems to be very, very much the same, but the exception being over in the tri-state area where you have all this Mississippi Valley type mineralization seems to be a unique area.
Right. Yeah, I was curious about the area with the Mississippi Valley type mineralization. Do you see any magnesite or talc associated with any of those deposits?
Maybe a little bit outside my wheelhouse. I think we're going to have to take on, and so I think that's the plan. So Sahar and Bob are going to have to take on another student just to tackle that area specifically, because it is different.
Right. Yeah. Okay, that was. Oh, and sorry. We have another question, Juan Pablo. Could you please send your email again?
Sure, I'll put it
So you
in.
have a request for some contacts there, which is great.
Yeah, please do reach out.
Okay, yep, so that's in the chat there for everybody. And is there any other questions from Jack? Do you have a question at all?
Well, I think it was a really, really great presentation. Really, really interesting. I suppose my one question would be, there's a big range of dates you have for your uranium lead. I know it's early days, but do you think, have you got any kind of thoughts on why there is, you know, such a huge difference in timing? You know, maybe there could be some remobilization of older brines later on.
Yeah, I love this topic. I would love to do a talk on just what can be done with the date, because it's really incredible. So some of the things, you know, I showed an example of that, you know, forms of Gondwana, formation of Pangea. But then we have lots of sort of events that happened between then and now. And so some of them, for example, like the severe orogeny, the laramide orogeny, these events also drove flow. So I'm sort of seeing some timing around those events. But then we have these really weird ones that are like this one. We have a 5 million year old calcite sitting in a 400 million year old matrix. So you have, you know, Cambrian rock, but clearly a really young cement in there that's hydrothermal with no real reason. So what it comes to mind is here in the Midcontinent, we've got this induced seismicity issue where human injection is causing earthquakes. And what that tells me is that you've got critically stressed faults that are ready to trigger now. And it probably these earthquakes have sort of been happening. So I'm thinking that there's a really good reason to believe that, you know, this is fault pumping, and that you have just an earthquake can just cause fluids to squirt up, and then there you have it. So yeah, super fascinating.
Definitely.
Yeah,
thank you.
That's great. We have the same thing up here in Western Canada. We're seeing the induced seismicity around these areas with dolomitization. Just one last question from Volker. Thank you, Andrew. Do you have the diagenetic, have the diagenetic fluids impacted the matrix significantly, or did they just leave cements?
Oh yeah, they definitely impact it. So I've got an example where they're dissolving out quartz late, you know, so it's not just reducing porosity, it can also enhance porosity, and I'm hoping to sort of be able to understand when is it which, but it is I do see both. So it's yeah, you can see oftentimes, you know, I'm focused in on, oh, there's a mineral, I can do stuff with that mineral. But certainly there's examples where in the petrography I say, oh wait, hey look, this fluid must have, it's got a hot mineral, it's got a hydrothermal mineral before, and then you've got a dissolution and then a hydrothermal mineral after. So that's probably a example of hydrothermal dissolution.
Right. Okay, great. Thank you very much. And we have another question, but we don't have time for it, so we'll get to that in our discussion session.
Sure.
Thanks, Andrew. Next up, we have our my co-chair, Jack Stacey, who's coming to the end of his PhD. He's going to be presenting some of his work from that PhD. He's from the University of Manchester, talking about dolomitization in Western Canada. Take it away, Jack, if you wanted to share your screen.
Okay, can you see that okay?
Yes.
Excellent. Okay, so today I'm going to be talking to you about the evolution of dolomitization over time in the Western Canada Sedimentary Basin. And in particular, I'm going to be talking about two case studies of fault-controlled dolomitization during the Cambrian and also during the Devonian. So first of all, what is hydrothermal dolomitization? There are examples of it found across the globe. But despite numerous case studies, there are many uncertainties. The origin of dolomitizing fluids, their volume, and also magnesium-calcium ratio. And these models often invoke ambiguous basinal brines or crustal fluids, which are really kind of characterized by highly saline, high-temperature dolomite fluid inclusions. And this was really kind of summarized and presented to the wider community by Davies and Smith in 2006. And their model really involves flux of hydrothermal fluids from the basement or basal-clastic aquifers up into overlying carbonate strata where dolomitization takes place along faults. Now, one of the main issues with this really is that dolomitizing fluid migration pathways are poorly constrained, in addition to the fact that we're not entirely sure where the fluids originate. And it's also assumed that fault-controlled dolomitization is a deep process, generally occurring during basin inversion or deep burial. But recent research has shown that you can have circulation of seawater down surface breaching faults into basal-clastic aquifers. So really this talk is sort of like just a summary of approaches and techniques to determine, one, the sources of the dolomitizing fluids, but two, the involvement of basal aquifers in dolomitization. And as I mentioned before, this will really be reevaluated by looking at fault-controlled dolomite in the Western Canada Sedimentary Basin. So as a bit of background to the Cambrian strata, so we're looking at the Middle Cambrian Cathedral Formation, which is effectively time equivalent to the Burgess Shale lager strata. And it's Middle Cambrian age, and it consists of pervasively dolomitized carbonate platform that's exposed in the thrust sheets of the Canadian Rocky Mountains. And it overlies the quartz aaronites of the Lower Cambrian GOG group. Additionally, along the platform margin, in this vicinity, in the Kicking Horse Rim area, we have MVT lead zinc mineralization. And then just as a comparison, comparing the Devonian strata, so the middle top of Devonian in age, we have the Swan Hills Formation, the Duke Formation, and Wabmun group. These consist of differentially dolomitized carbonate platforms, reefs, and ramps in the subsurface of Alberta, as shown in this figure here. This strata overlies various carbonating clastic aquifers of different ages. And these dolomitized reefs host large volumes of conventional hydrocarbons. Now, there's been a lot of previous work done on this, and as such, there's a rather large geochemical database that's kind of available if you have the patience and time to put it all together. So really, this study is kind of summarizing that data and reevaluating it through a meta-analysis. So first of all, we have dolomite phases in the Middle Cambrian, which are replacement dolomite phases, numerous phases here, that are cross-cut by stylolites, which would indicate they formed at around less than 300 meters depth. We also have saddle dolomite cement present, and also orthogenic quartz. And both of these phases cross-cut stylolites, which indicate that they formed at greater than 300 meters depth. Now, all this means really is that there was a Middle Cambrian timing of dolomitization and saddle dolomite cement precipitation. And then just compared to the Middle to Upper Devonian, we also have replacement dolomite phases, but they're not cross-cut by stylolites. They actually cross-cut the stylolites themselves, which suggests they formed during shallow burial. Additionally, saddle dolomite also cross-cut stylolites and contains hydrocarbons, which suggests that it formed during deep burial, as hydrocarbons were only being generated in the basin during deep burial. And from this, we can say that replacement dolomitization likely occurred from the Devonian to the Mississippian, and saddle dolomite cement from the Cretaceous to Paleogene. Okay, so now that we've established that, let's just go into more detail about the dolomitizing fluids themselves. So the Cambrian dolomitizing fluids that we've identified through rare earth element analysis, replacement dolomite is seawater. It's characterized by negative cerium anomalies and positive yttrium anomalies, whereas the saddle dolomite phases are completely different. They have this quite strange light rare earth element depletion and enrichment in middle rare earth and heavy rare earth elements. And these have actually been documented for hydrothermal dolomites in various MVT districts, including the viburnum trend in the US. And then when we plot up the cerium anomalies, essentially this quadrant here represents seawater, and down this corner is most similar to seawater. We see that, as you'd expect, limestone is most similar to seawater, but then we have this progressive backstepping and of different replacement dolomite phases. And this would suggest that seawater was dominant during the early replacement dolomitization, but reduced over time. Now, additionally, we ran clumped isotopes on these samples, and we have dolomitizing fluid temperatures of up to 238 degrees. Additionally, the delta 18O water values of these phases indicate the involvement of crustal fluids, as shown here, rather than Middle Cambrian seawater, as you possibly expect. And additionally, we ran noble gas analysis in these samples, and the krypton argon and xenon argon data are consistent with serpentinite-derived brines. So in comparison, to compare that to the Devonian dolomitizing fluids, again, we used rare earth element data to show that replacement dolomite formed from seawater, whereas saddle dolomite, because it doesn't fit within this quadrant, formed from basinal fluids. And these phases formed at between 32 and 86 degrees C, whereas saddle dolomite formed between 90 and 195. Now, in order to really kind of constrain where these basinal fluids came from, we looked into reservoir pore fluids, specifically those that contain high lithium and strontium concentrations. And interestingly, these fluids are highest in areas where we think there's been some interaction with clastic aquifers in the Precambrian basement. And the fact that they're depleted in magnesium would suggest they were potentially involved with dolomitization in the past. And actually, we recognize these now as residual Middle Devonian evapoconcentrated seawater that interact with clastic aquifers and the Precambrian basement in various places. So how do we figure out where these fluids have actually come from? So we undertook X-ray diffraction of some samples, and we found that this is just an example from the Cambrian. We have quartz and albites that are more abundant in dolomite than limestone. And additionally, in the aquifer beneath the Cambrian cathedral formation, we have dolomite cement, which would suggest potentially that if you have flux of fluids through this basal aquifer, it was potentially picking up quartz and albites before they were reprecipitated in the cathedral formation overlying it. And we use the same approach really for the Devonian example, where we compiled strontium data from across the Western Canada Sedimentary Basin. And in areas where we have incredibly high, i.e. radiogenic strontium, along with the association of quartz and albite with dolomites, it would suggest that we have fluids that have previously interacted with basal clastic aquifers, whereas in areas where we have non-radiogenic strontium and no quartz and albites, would suggest that they have interacted with the basal carbonate aquifer. So in terms of the dolomitization model for the Cambrian, this is what we propose was happening, was that you had this updip migration of hot serpentinite-derived brines. You had descending cooler seawater. You also had fluid circulation and regional scale migration within the GOG group as well. And then just to zoom into a bit more detail, our study area in particular, what we interpret with the strong negative cerium anomalies indicative of seawater in the earliest phase of dolomitization, we interpret it to be that the fault was breaching the surface, and that's why the cerium anomaly was strongest, so you're having more seawater at time 1. Then at time 2, the negative cerium anomalies become progressively less strong over time. So we've interpreted that to really suggest that there's been a shutdown in the supply of the seawater, and this really is kind of interpreted to reflect deposition of the overlying Stephen Formation shale, which effectively blocked the fault off. And then finally, in the final stages, what we have are the formation of saddle dolomite cemented breccias, which is kind of like the last gasp of the system. After this, we don't get any more matrix dolomitization, because presumably the fluids could no longer migrate upwards into the cathedral formation. And then to compare this to the Devonian examples, what we have in the West Shale Basin, so just in this area, this is the area that I said had, thank you, radiogenic strontium, quartz and albite. So we've interpreted that to represent the fact that you've got dolomitizing fluids that have interacted with basal-clastic aquifers before dolomitizing overlying carbonate strata. And then conversely, in the East Shale Basin, because there's no radiogenic strontium or orthogenic quartz or albite, bar minor examples, we interpret this that there was a basal carbonate aquifer before fluids migrated upwards and dolomitized overlying carbonates. And then finally, in the Peace River Arch area, we have a similar situation that we have the radiogenic strontium and orthogenic quartz and albite with fluid migration up faults into overlying carbonates too. So really, what are the conclusions and implications for this? So first of all, the studies have found that dolomitizing fluids in the WCSB are identified as seawater in both the Cambrian and Devonian. Serpentinite-derived brines are present in the Cambrian, and then we also have residual evapoconcentrated seawater during the Devonian. It's also recognized that hydrothermal dolomitization can occur at very shallow depths, and that fluids magnesium-calcium ratios can be increased by serpentinization. Long-distance fluid migration may require basal aquifers, and the involvement of these aquifers can be determined by orthogenic quartz and albite and radiogenic strontium. And then a regional approach to geochemical data is necessary to determine the fluid origins and migration pathways, which ultimately reduces the ambiguity of fault-controlled dolomitization models. And finally, I'd just like to say thank you to everyone that's collaborated with me on this, particularly Hilary Corlett and Kathy Hollis, my supervisors, also Adi Kawishidi-Otola, Fiona Whittaker, and Hamish Robertson as well. Thank you very much for your time, and I'm looking forward to your questions.
Great, thank you very much, Jack. And we can keep that slide up to advertise your publications there. And we have the chat now open. So if anyone has any questions for Jack about this wide array of work that he's done, it was quite a lot of work, I can attest to that. You can just pop that into the chat. Remember that you send your questions to everyone. And I'm just going to ask a question of Jack, now that you're coming to the end of these studies. If you had a bunch of money and 2 more years, what would you focus on next in terms of answering some questions here? Because it seems like you've answered a few questions and probably generated a lot more.
Yeah, so I think you know, following on from Andrew's talk, really, is that I think the application of uranium lead dating would be really interesting in this case, because I think it would be really cool to see, you know, although we've kind of constrained relative timings of dolomitization and saddle dolomite precipitation and things, it would be really interesting to see when exactly that happened. And also, I think for me personally, it would be really interesting to see how rates of dolomitization vary. So hydrothermal dolomite, are huge areas dolomitized really rapidly compared to other examples of dolomite because of the higher temperatures and the kinetics behind that. So I think, yeah, that would be my next step if I could, but unfortunately there's never enough money to do these things.
Yeah, we'll have to see how Andrew's study works out with the uranium lead dating, sorry. Is there any questions out there? I haven't seen any questions come in yet. Oh, actually, sorry, there is one here. Spoke too soon. From Bruno Lima. Jack, very interesting job. Is most of the porosity formed in the last phase of dolomitization under burial conditions?
I would actually say that porosity tends to decrease over time. So particularly with the hydrothermal examples, what we see is like a progressive recrystallization, coarsening of crystal textures. And then obviously you have these very coarsely crystalline saddle dolomite cements. Really, the earliest stages are generally the most porous. It's quite hard to tell in the Cambrian example because it's all packed stone, it's pretty tight. So the likelihood is that it had quite a low porosity to begin with anyway. But with the Devonian stuff, what we see there is a lot of dissolution of allochems and things. And in that case, it seems to be the porosity was forming earlier. And again, you had the emplacement of cements along faults and things. So really, I think in my mind, porosity is forming early, and then you're having these porosity destructive processes happening later on, typically.
Right. So then that would also maybe imply that the earlier dolomitization events are maybe more widespread, and the saddle dolomites are maybe more localized, would you say?
Yes, certainly. Yeah, certainly. Yeah, from what we've seen in the field, you can have replacement dolomite bodies up to 6.5 kilometers, whereas the breccias that are rather cemented by saddle dolomite only exist on a scale of tens of meters, very proximal to faults.
Right. Okay, we have a few more minutes for questions. If anyone else has a question out there, feel free to pop it into the chat. Oh, we have one question here. Okay, from Cole McCormick, leading question here to expand on Bruno's question, but how would you compare your observations of poroperm to that of Davies and Smith 2006 publication?
Yeah, so I would say that from the Davies and Smith model, you would expect to find the most porosity along faults. And this was kind of related primarily to some sort of acidic dissolution going on with hydrothermal fluids. But what we really see is the complete opposite. It's very tight in the vicinity of faults, and really, you couldn't ask for a worse reservoir, really. You get very isolated bugs, but you might see a couple over a couple of meters. And in that case, you're not going to get any kind of meaningful flow through there. And then on top of that, it is fractured, but there's no real capacity for containing, hydrocarbons in any sense.
Okay, thanks. And we have a couple more questions rolling in here. So from Alexia Anastas, one of the big issues with burial dolomite is size and extent of the dolomitization. Do you think the entire platform margins can be dolomitized with solely HTD, or must there be an evaporitic component to the dolomitization?
That's an interesting question. I think what it comes down to in terms of burial examples is the initial porosity. So there are lots of examples in the Devonian of the WCSB where you effectively have these regional scale conduits, and really that you can dolomitize huge areas, provided that you can flux the fluids through them. I think one of the issues really that we're still kind of grappling with is that there may well have been an earlier phase of dolomitization that might have been related to, say, burrows that acted as seeds. And actually some of Ardy's work, who he's published in the last year or so, what he's shown basically is that in lots of examples, you can have burrow-controlled dolomite, and then the subsequent flux of dolomitizing fluids, whether it be reflux or HDD or whatever else, effectively kind of joins that all up. So that acts as seeds and just accelerates the whole process. But no, it's a good question. I think, there still needs to be a bit more work done on that.
Great, thanks. And we just have 1 minute left, or maybe less, but just quickly from Zi Yang, great job, Jack. Is there any petrographic evidence to prove MgCa increased by serpentinization or other geochemical signatures?
That's a really good question. And that is a bit outside my wheelhouse, I'm afraid. So Hamish, who worked with us on this, he's been looking mostly at freak modeling, and basically has showed that the whole process of serpentinization can produce very magnesium-rich fluids. But in terms of me quantifying that from this, I'm not entirely sure. Sorry.
Okay, great, thanks. And Fiona just makes a suggestion that lithium may be something to look at. Yeah, we do see the lithium corresponding to a lot of these areas that have been dolomitized, certainly in the Devonian examples. Okay, great, thanks, Jack. I think we've reached the end of the deeper Diagenesis session. So thanks to everyone for attending, and thank you very much to all of our speakers for sharing your wonderful work with us. Thanks also to my co-chair, Jack Stacey. And I believe the next thing in the schedule would be a coffee break and discussions. And then at 3:40 UK time, we have the forum discussion with Nick Tosca, Sasha Turchin, and Rachel Wood on the role of carbonates in the global carbon cycle through time. So first off, we have our coffee break and discussion room where we can go and discuss any of the talks that we saw in this session or throughout the day a little further. And then we'll get into our last sort of forum discussion for the Carbonate Forum event. I'm not sure if